Hi, I'm Jan-Orlarey. In this talk, I will present an undergoing research project diagram aiming at developing a new intermediate representation for the Faust compiler. The main motivation of this work is that the current structure of the compiler is quite difficult to modify. As a result, it is very complicated to change the code generation strategy. The goal of this new intermediate representation is to give us much more flexibility for implementing and testing new code generation strategies and new optimizations. Here is the agenda. I will start with the current approach. I will present how, in its broad lines, the Faust compiler works. In particular, I will explain how the process that leads from Faust code to C++ code involves several successive transformations and various intermediate representations. Then I will explain why the current organization of the compiler, even if it works very well, is problematic. I will then present in details the new intermediate representation as well as new code generation strategies that it permits to achieve. I will then give the results of benchmarks comparing the current Scala code generation with these new strategies. And finally, I will conclude and give some perspectives. Let's start with the current approach. Once the Faust code has been fully parsed, there are 5 main steps. The first step allows us to go from the algorithmic description of an audio circuit to its representation in normal form. Then we have the symbolic propagation phase, which allows us to calculate the equation of the output signals as a function of the input signals. These signals are then simplified. All the calculations that can be made at this stage are done. We obtain signals in normal form which cannot be simplified any further. Then these signals are compiled into a FIR, the Faust imperative representation, a kind of idealized imperative programming language. Finally, the FIR is translated into the target language corresponding to the selected backend. Let's come back in more details on the symbolic propagation phase, because this will allow us to better understand the problem. Let's first look at the propagation in a sequential circuit. So this is a sequential circuit. Let's say that we propagate S1 and S2 into F. Then the output of the F circuit will be F of S1, S2. That feed into J, and the output will be J of F of S1 and S2. Very straightforward. Now, let's see the propagation in a circuit with a feedback that will give rise to a recursive definition. It's much more complicated. Imagine that the input signal is S1. Then we need to allocate a name to the output signal of F. Let's call it R. Then if this signal is R, this one is R delayed by 1 sample. So let's write that, delay R 1 sample. The output of J now is J of delay of R of 1 sample. Now we can compute the output of F, which is F of J of delay of R by 1 sample and S1. So now we have the equation of the R signal. So let's see how the R expression is represented internally. We use a representation that is very close to a lambda term. Here the node mu R indicates the definition of R, which refers recursively to itself here. This is a way to indicate a cycle without physically having to create a cycle. In reality, we start with a Debrun representation of the tree, which avoids having alpha equivalence problem to deal with. And then we convert this Debrun representation into symbolic representation in order to optimize the sharing of expression by hash counting. So what are the problems with this approach? Well, this way of encoding the cycles doesn't leave us with many possibilities to traverse the expressions. We always have to start at the root because we have to memorize the recursive symbols as we encounter them. Almost all compilation decisions have to be made during the recursive descent into the tree. This leads to a very complex code. Finally, it is complicated to experiment with other approaches, especially if one wants to schedule the code in a different order. To regain flexibility, we have introduced a new intermediate representation between signal expression and FEAR code generation. It's a directed graph of instructions. Now, the recursive descent in the tree is much simpler. It has only one decision to make, which is to separate expressions into instructions. The resulting graph can be manipulated and traversed using classical techniques of cycle detection, topological sorting, etc. The visit of the graph is very simple and no longer linked to the structure of the expressions. In this new approach, an instruction is a way to indicate that a signal has to be written in memory. For example, an output signal has to be written in memory into the corresponding audio buffer. A delayed signal has to be written in memory into a delay line, and a shared signal expensive to compute has to be written in memory to avoid being recomputed. All these decisions are almost universal and independent from the target language or additional optimizations. When an expression is transformed into an instruction, its occurrences in other expressions are transformed into memory access, like here and here. The transformation algorithm is described by a set of rewriting rules. All output signals, for example, are transformed into output instructions. And the transformation is applied recursively. For example, the last rule here says that the delay signal is transformed into an instruction that writes the signal in memory and an expression that reads the delayed signal from memory. These instructions form a directed graph with potential cycles. To implement these graphs, we have developed a small library available on GitHub. The API is very simple. You start by creating an empty graph, then you add nodes and connections between these nodes. Note that the connection carries a numerical weight that indicates the time dependency between two nodes. By default, the dependency is immediate and its weight is 0. A weight of 1 indicates a dependency on the previous sample of the signal. The navigation in the graph is very simple also. You can iterate the nodes of a graph and then you iterate the connection of a node. The library implements classical algorithm. For example, graph2dag transforms an arbitrary graph into an acyclic graph of cycles using Tarjan's algorithm. Cut removes all connections with a weight greater or equal to n. For example, we know that if we cut all non-zero connections of a Faust graph, the resulting graph is a DAG. Parallelized transforms a DAG into a vector of vectors of nodes, and serialized transforms a DAG into a vector of nodes. Let's see concretely what happens on an example here, Karplus strong. Note that this Faust code has 4 delay lines, 3 of which can be merged. The delay line here, the delay line introduced by the feedback, and the delay line used for the average. Here is the graph resulting from the transformation of Karplus strong signals into instructions. This graph can be further optimized. Note that there are already only 3 delay lines remaining: R0, D0, and R1, and that R0 and D0 are mutually dependent and can be merged. This is what happens here. R0 and D0 are merged into a single delay line of 81 sample, that is 79 plus 2. In this transformation, delay lines are replaced by read-write tables with appropriate index expressions to implement ring buffers. Finally, common sub-expressions are factorized. This graph will finally be translated into fear after being scheduled, that is, sequentially organized in any order that respects the instantaneous time dependencies between instructions. As we just said, scheduling instructions is organizing the instruction of a graph sequentially, but in such a way that instant dependencies are always respected. A given instruction graph can therefore have several possible schedulings. We can wonder if some schedulings are more efficient than others. To find out, we have implemented and tested 6 scheduling strategies, which I will present briefly. In mode 0, we proceed in 2 steps. We first transform the graph into a DAG whose nodes are potentially cycles, and we serialize it. Then, for each cycle, we cut the connections with weight greater than 0 and serialize it. Mode 1 is the simplest one. We just cut all connections with weight greater than 0 and we serialize the resulting graph. In mode 2, we also cut all connections with weight greater than 0, but then we parallelize the resulting graph and we emit the fear code in a breadth-first manner. In mode 3, we cut all connections with weight greater than 0. We serialize the resulting graph, but with priority on output instructions. In mode 4, we cut all connections with weight greater than 0. We serialize the resulting graph, but with priority on delay lines and emit the fear code. Finally, on mode 5, we use a deep first traversal with priority on output instructions and immediate dependencies and emits the fear code. To test the efficiency of these new modes, we took 26 Faust programs from the examples and compiled them in scalar mode and in these 6 new modes. The following graphs show the variations in relative performance. The reference 100% is the performance of the scalar mode. Higher values correspond to better performance. In mode 0, you get an average performance improvement of 20%, with performances almost doubling on French Bell here and on tuned bar 6. In mode 1, the behavior is similar, although the average improvement is slightly lower at 19%. As we have indicated, mode 2 uses a very different scheduling on a previously parallelized graph. The results are much more contrasted, with performances that degrade for bubble or free verb, but that are the best for spectral level and violin MIDI. Mode 3 is similar to mode 0, but almost systematically slightly lower. The same is true for mode 4, although it improves the performance of mode 0 in a few cases. The same goes for mode 5, although it also improves some of the performance of mode 0. Now, if we compare all the modes except mode 2, we can see that mode 0 is the one that improved the overall performance the most, with plus 20%. But mode 2 is also sometimes interesting, as with filter bank, violin MIDI, and virtual analog, where it significantly improves the performance of mode 0. As we can see, there is no one scheduling strategy that is the best in all cases. Nevertheless, if we compare the scalar mode with the best mode for each example, we get an improvement in 21 cases, with an overall improvement of 30%. In 5 cases, the improvement exceeds 50%. It is interesting to note the following. Apart from the traditional scalar code, the only difference between all these new modes is the scheduling, the order of the computations. The computations are exactly the same. It is just the order of the lines of code in the generated C++ program that change. And yet, the impact can be considerable, up to 68% of performance improvement for Karplus 32 between mode 2 and mode 5. Of course, we know the sensitivity of modern processors to memory access and cache conditions, but here we can clearly see that these more macroscopic optimizations are not performed by GCC. Hence, the interest of having a Faust compiler to test this kind of code reorganizations. As we just shown, the simple fact of being able to change the scheduling of the generated code has a considerable impact on performance. This was made possible by the introduction of a new intermediate representation. This representation is based on a notion of instruction, which simply indicates that a signal has to be written in memory. The instructions form a graph representing the time dependencies between these instructions. This graph structure is much more flexible, and it is easier to implement new optimization and schedulings. These new schedulings, as we have seen, have a significant impact on performance. But for the moment, all this is still at the experimental stage. Before being able to merge it into the master dev branch, we will have to implement the vector and parallel modes. But with the vector mode, we will be able to test a new kind of optimization, consisting in cutting long-term recursive dependencies beyond the size of the vector, in order to allow more vectorization and parallelization opportunities. Finally, we plan to integrate another experimental development, the on-demand primitive, which allows to control when computations are done, for example, to do upsampling and downsampling. Thank you for your attention.